We will continue looking at some examples of exponential growth and decay type of problems. And the previous examples were mostly financial, okay, investments, that sort of thing. Starting with number 9 here, we're not looking so much at money or financial examples, but populations. So, for example, number 9 is about the number of bacteria that are in a culture, like in a petri dish or something. But the same idea would work if it's, population of a country or a town, population of animals that live in a certain area, etc. Most of the time, it is an exponential scenario. Now, as a reminder, the formula, A of t, so the amount at some point in time, equals A sub O, the starting amount, times e to the kt. Remember, k is the rate of either growth or decay, and t is the time. Notice that is basically the exact same formula as the PERT formula. Okay, so P is your principal or the starting amount. Still have E, still have R for rate, or K is the rate if you're using this version, and then T is for time. So it's the same formula. I typically just think of it as PERT just because I remember that one from the financial continuous compounding problems. Okay, and it is continuous compounding because when you're looking at population of bacteria or whatever the case may be, it is continuously growing. It doesn't say, oh, it's just going to compound once a week or once a month or whatever. It's continuously happening that new bacteria are being born or dying out or whatever their pattern is. Okay? All right, so the number of bacteria, N is the number of bacteria, present in a culture at time t in hours. Now notice, time is based in hours. So apparently these bacteria grow exponentially, they reproduce in a matter of hours as opposed to days or years or weeks. Like within the financial ones, we typically use time was in years. But when we're doing populations, it could be some other measure of time, and they are telling us here that it's time in hours. And it obeys this function right here. So N of t is the amount of bacteria at time t. Okay. Now notice they have put 1,000 in the A sub O, or the P value spot right there. So that must mean we're starting with 1,000. That's how many bacteria were in there initially. There's our E. The rate is 0.01. That would be 1%. And then our time, T, of course, represents hours. All right, so part A, determine the number of bacteria at T equals 0 hours. So they are telling us to take this formula and plug in 0 for T. So N of 0 is 1,000 times e to the 0.01 times 0. We're putting 0 in for t. We can just plug this into our calculator. 1,000 times e to the 0.01 times 0. Remember the e button, if you'll push second, and then the ln, which is next to the 4, it will give you the e, and then you can raise it to whatever exponent you wanted. Okay? And it tells us that comes out to 1,000. Now, we should have known that it was going to be 1,000 because we could tell by the format of this equation that the initial population, the starting amount, was 1,000. Okay? So, the initial population is 1,000. And again, we should have known that before we typed it in because 1,000 is in that principal or starting amount position. What is the growth rate? Remember, rate is the K, or if you're using PERT, it's the R number. So they have 0.01 in that spot. Now, 0.01 is the decimal. If you want to convert it to a percent, you'd have to move that decimal twice. So it's 1%, and I'm going to point out that it's growth. The population is growing by 1% every hour. And the reason I know it's growing is because it's a positive number. If that exponent right there had been negative, then that would be indicating that the population was decreasing, was going down. Part C, what is the population after 4 hours? They are telling us to put 4 in for T. So 1,000 times e to the 0.01 times 4. We're putting 4 in for T, 4 in for our hours. So put 4 in for T, and we can type that in our calculator. 1,000 times e to the 0.01 times 4. If you're using an 83 calculator, you will need to put the 0.01 times 4 in parentheses so that it knows that whole thing is your exponent. All right, so N of 4, that means when the time is 4, the population will be 1040.81 blah, blah, blah. Now, keep in mind this is a population. So you're probably, if it was people, you would not have 1040.8 people. If it was, number of jackrabbits that live out in a field or something, that'd be a lot of jackrabbits. But if it was, you probably wouldn't have 1040.8. So generally when we're dealing with populations, we're going to round to the nearest whole number. Just makes more sense. So I would round that to 1041 to the nearest whole number. That'd be 1041. So in 4 hours, the population will be about 1041. Now I am going to say about or approximately, okay? This is an estimate. If it was 1042, I would not be shocked. If it was 1039, I would not be shocked. But it should be right around there, assuming nothing has changed in the equation. No penicillin has not been introduced into the population of bacteria. They weren't given extra, stuff to feed off of or have a temperature change or something like that. But if nothing changes, it should be right about 1041. When will the number of bacteria reach 1700? Notice they ask us for when. They're asking us to find T. So if we go back to our formula, and notice I'm using n's, just because, the starting amount, that they're using n in that formula right there, e to the 0.01 t. So we're ending with 1700. 1700 is going in for the n of t. And we're solving for t. We've got to get the exponential part by itself, so we'll divide by 1,000. So we're going to have 1700 divided by 1,000, and we get 1.7. So 1.7 equals e to the 0.01 t. The exponential portion has been isolated, but now we need to get not just the exponential, but the actual exponent by itself. And to do that, we convert to a logarithm. So log base e, but we don't write log base e, we just put ln. ln means log with a base of e, of 1.7 equals 0.01 t. And then to get t by itself, we divide by 0.01. This does not mean that 1.7 is getting divided by 0.01. It's the entire ln of 1.7. Whatever the answer to that is, that's getting divided by 0.01. So ln 1.7, divide that by the 0.01. And we get 53.0628 blah, blah, blah. They will tell you in the prompt what to round to, if they want you to round to the nearest whole number or the nearest tenth of an hour or whatever. So let's just say hundredths, just for practice with 2 decimals. So 53.06, and it's in hours because they told us in the prompt that they were using hours for time. So it would take about 53 hours for the population to go from 1,000 bacteria to 1,700 bacteria. And then they ask us in part E, when will the number of bacteria double? Now, we could say, well, if we're doubling, that means we're going from 1,000 to 2,000. So we could solve this equation right here for T. Or we could notice, oh, doubling, they want us to use our shortcut. So remember, our doubling time was ln2 divided by the rate. And in our case, the rate was that 0.01. So T equals ln2 divided by 0.01. ln of 2 is this terrible, horrible decimal, divided by 0.01, and we get 69.3147. You'd have to round to whatever place value they said. If they said hundredths, then it would be 69.31 hours for the population to double. Okay, this one is a human population. So countries, if you think about a country, they're constantly having new citizens being born, which increases their population. They're having citizens die, which decreases their population. And then they have people move in and move out, okay, immigration. And that causes the population to go up or down depending on whether the people are moving in or moving out, okay. So the country of Brazil, it said, had 52 million people in 1959. and 91 million people in 1979. When you do your homework, a lot of times that's going to be presented to you in a chart form. It might say the year and the population. So it might say, okay, well in 1959, we had 52 million, and in 1979, we had 91 million. And I'm going to leave off all the zeros for 52 million. I'm just going to know that I'm working with millions of people, that they've rounded to the nearest million, okay? So one thing I would notice is from 1959 to 1979, 20 years have passed, okay? And then the population has gone from 52 million to 91 million. So it has gone up by 39 million people. It's been an increase of 39 million people, okay? Now, the first thing they ask us to find is the growth rate. So in our formula, if you use the PERT formula or the A formula, R is your rate, or if you're, R is your rate if you're using PERT, K is your rate if you're using this one. Same idea though, okay? And they specifically say to round to 3 decimal places. Now I would point out, we are going to wait till the final answer to round to 3 decimal places. Any scratch work steps, we need to keep all the decimals, so we will leave those stored in our calculator, okay? All right, so I'm going to, they don't say it this way exactly, but I've got a starting population and an ending population. My starting population, we're going to say, is 52 million. I'm just going to put 52, but I know that's in millions. My ending population is 91. Now, I know that's not the end of the country of Brazil. It's not the end of the world, but it's the end where we have data, okay? So started at 52, ended at 91 in this formula in the data that we have. Times e to the kt. I do not know the rate, so I'm going to leave that as r or k, whichever one you want to use is fine. And our time is going to be 20. 20 years passed. So in the 20-year span from 1959 to 1979, that was 20 years, and our population went from 52 million to 91 million. Okay? So my rate, I can solve that for k. So I'm going to divide both sides by 52. 91 divided by 52 is 1.75. I need to use that whole value. 1.75 equals e to the kt. If it's okay, I'm just going to call it 20k or 20r if you want to use r for rate. Now we need to solve for k. This is an exponential, so I can convert to a log. Log base e, or just ln, of 1.75 equals 20k. Divide both sides by 20, and that will get k by itself. So ln 1.75, divide that result by 20. Notice I did not round off the 0.5596. Do not round it. If you round it off here, you will lose accuracy and will not be accurate to all your decimal places in your final answer. So leave that 0.55 number in there and hit divided by the 20, okay? And then here is where I can finally do my rounding because I have my final answer. So 0.028. And the reason I'm saying 7 is in, 7 is the third decimal. The number after that, which in this case is 9, tells me whether that 7 goes up or stays, and it goes up. So 0.028 is my k. Make sure you read carefully on your homework. Do they want the rate as a decimal? If so, then you would put 0.028. If they wanted it as a percent, then that percent would be 2.8%. So they could ask for it either way. Just make sure you read which way they want it, as a percent or as a decimal. Now, because the rate is a positive number, we know that the population is increasing. And we already knew that because we saw that it went from 52 million to 91 million. The population definitely went up. It increased. So our rate should be a positive number. Okay, part B, they want the exponential growth function, okay? So we're going to say our population, our A of t, will be the starting population, which is 52 million, times e to the 0.028t, okay? 0.028t. Now, couple of ways you could think about it here. I'm leaving it as 52 to represent, I know that this number is in millions. If you wanted to actually write out the entire 52 million, you could. 52 million would be 5200000 e to the 0.028t. Okay. If you write out the entire 52 million, then if you plugged in a certain time, what came out would be rounded to the nearest person. If you leave it at 52 instead of writing all the zeros, then when you plugged in a certain time and worked it out, what would come out was how many people there are rounded to the nearest million. And we'll look at an example of that in just a second. All right, part C, how long will it take the population to double? Well, that's our doubling formula, ln2 over the rate. They told us the rate, or we calculated the rate to be 0.028. So ln2. Don't round that off. Leave that whole decimal there. Just hit divided by 0.028, and we get 24.755, which would be approximately 24.8 years. And again, you just have to see what they want you to round to. They want you to round to the whole number, then that'd be 25 years. They want tenth of a year, then it'd be 24.8 years, etc. And then part D, what should the population be in 2009? Okay, well, notice 2009 is 50 years from 1959. Okay, so we're going to put in 50 for T. So my amount in 50 years will be 52 times e to the 0.028 times 50. Putting 50 in for T. I'm taking this formula and putting 50 for T. So 52 times e to the 0.028 times 50. Remember, if you're using a TI-83 calculator, you need your 0.028 times 50 all in one set of parentheses. All right, and we get 210.9 if I rounded that off to the nearest tenth. Now remember, that's not 210 people. It wasn't 52 people. It was 52 million people where they started. So this means 210.9 million people. That would basically be 210,900,000 people. Okay, round it off. Now, if I use the entire 52 million and said, hey, this was probably not exactly 52 million exactly, but approximately right here, e to the 0.028 times 50. Now this is to the nearest person, so it's 210,870,398 people. But notice that would still round to 210,900,000. Okay, so you just have to kind of read, do they want you to round to the nearest person, or to the nearest million, or the nearest 100,000? What do they want you to round to? Okay. All right, population growth, one more example here. This is a population at a college, okay, number of students enrolled at that college. Follows exponential law, that means it's using this exponential growth formula. The initial population was 1,500. After 10 years, the population increased to 7,000. What is the projected population of the college after 18 years? And what is the doubling time? Okay. So our initial amount, I'm going to use P for principal, even though I know it's not money, but I'm going to use P because I'm going to use the PERT formula, was 1,500. After 10 years, so when T is 10, your ending population, your A, is 7,000. Now notice they give us the A, the P, and the T, but they don't give us the R. So if we're going to want to predict a population at some point in the future, we're going to need to know the R. So I need to find R. So I'm going to start out with 7,000 equals 1,500 times e to the r times 10. And I can solve this equation for R, for the rate. So we'll divide both sides by 1,500. And here's where we have to be careful. 7,000 divided by 1,500 is not a whole number. It's not even a rounded off decimal like 4.6. I cannot round this off. If I round this off, I will lose accuracy when I find the R. So I'm going to write 4.66667 equals e to the 10r. But I am not going to type in this rounded off value. I'm going to make my calculator use all those decimals, okay? All right, so solving for r here, I'm going to have to convert this exponential to a log. So log base e, or ln, of 4.6666 equals 10r, and then I'd have to divide both sides by 10. That will be my rate, okay? So ln, and if I can't just type 4.66, if I type that in, I'm going to lose some accuracy. So if you're using an 84, you want to arrow up, grab that number, and let it paste it in for you. If you are using an 83, you would hit ln and then second answer, and to get that, you hit the negative key down here, and it would repaste that whole thing. Or you could just type ln and type every bit of that, all the 6s all the way to the 7. Okay? All right, but you do not want to round that number off. All right, this 1.5, I don't want to round that off. That number needs to get divided by 10. So I just hit divided by, and it knows to take that answer and divide by the 10. So my r is 0.15404, blah, blah, blah. Okay? Now, at this point, if they asked for my rate, this would be the point that I could do that. Okay? So my rate is 0.154. If they asked you for the rate, that's where you could round it off. Okay? So then they say, what's the projected population of the college after 18 years? Well, in 18 years, that means your t is going to be 18. So I know in my PERT formula that I can now put the 0.154 as my rate. And I'm looking for the amount in 18 years. So I'm looking for A. I'm looking for that ending amount when we start at 1,500 and E is raised to the 0.154 times time. And then time in this case is 18 because they said, what is it in 18 years? So this is what I'm going to type in my calculator. Starting at 1,500 times E raised to the rate times time. And the rate is 0.154 times my 18 years. So my population at the end of those 18 years should be 23,986. And I'm rounding to the nearest whole number in this case because it is people. It's how many people, what's the population of that school. So in 18 years, population is about 23,986. Okay. And then they also mention what's the doubling time. We can use our little shortcut formula. Time equals ln2 over the rate. Our rate was 0.154. So ln2 divided by the rate of 0.154. So the doubling time is 4.5 years. By the way, I didn't mention this, but because the rate is a positive number, we know that the population of this school is going up. It is increasing. If the rate had been a negative number, that would mean the population at the school is decreasing. Okay. Here's another real-life example of how exponential functions can be used. You maybe seen on the news or different stories, maybe they find dinosaur bones, or maybe they find some kind of cave where there's some evidence of human remains, like pottery or a painting or something like that. So here's an example. They find some cave paintings in France, and 2% of the carbon-14 remains. How old is the sample? Okay, so they know humans were there because there's some paintings or something like that on the wall. And then maybe they find some old bones or something like that, so they know that people were there. Now, carbon-14 is an isotope of carbon. It's a certain type of carbon that they know live in, living things like people or plants or whatever. And so they know how fast carbon decays. They know the half-life of carbon. They know how fast it decays. So based on maybe the size of the bone or the size of the human remains, they know, hey, about 2%, whenever this thing was alive, it had however much carbon, and we know that it's probably got about 2% of what it started with left. So they can work backwards and figure out how much time has passed, and if they know how much time has passed, then they know how old the sample is. Okay, so how long ago those people died from that culture, from that time period. Okay, So here's their formula. I know it's that PERT formula, okay? Now they aren't using P, they're using P for principal, they're using QO for the starting amount. And then Q of T would be the ending amount, okay? So they do not tell us the starting amount and they do not tell us the ending amount, but they tell us that only 2% remains. So here's what I'm going to do. I don't know how much they started with. I'm going to leave that as QO. That's my starting amount. I do not know how much it is. But I know that if I multiply it by 0.02, that will be how much I ended with. For example, let's say that you started with 50 grams. If you multiply 50 by 0.02, that means you ended with 1. If you started with 1,245 and you multiply by 0.02, then that means all those years later they're ending with 24.9. So I don't know what the starting amount is, but I know that my ending amount, my Q of T, equals 0.02 times, sorry, I'm not writing this the way I meant to. Sorry, I had a moment. Sorry. My starting amount, QO, times 0.02 is how much I'm going to end up with. So I end up with 0.02 times QO. That's what I meant to write. Sorry about that. Okay. So I ended up with 0.02 times whatever that starting amount was. Now that starting amount was e to the negative 0.000, that's 3 O's there, 121t. Okay. So watch what happens here. When I divide by QO, my starting amount, I end with just 0.02. So I'm ending up with 2%. That 2% is e to the negative 0.000121. Okay? So basically, you know, if I started with 50 grams and I multiplied by 0.02, I ended with 1. 1 would be my starting or my ending amount over here. If I started with 1245 times 0.02, I ended with a 24.9. 24.9 would be this ending amount. Okay? So I'm basically just saying, hey, I'm ending up with 2%. I'm ending up with 0.02 of whatever it was. Okay? Now I can solve this equation for t, and I will know how much time passed between when this human artifact died and all the years later when we finally find it. Okay? So I would also point out that this rate is a negative number. That means the amount is declining, it is decreasing, which we expect because they told us only 2% remains. All right, so to solve this, I need to convert to a log. Log base e, which is just ln, of 0.02 equals negative 0.000121t. To solve for t, I divide by negative 0.000121. And that should give us our t. So ln 0.02 divided by negative 0.000121. And it comes out to 32330.768, whatever, okay? Now, it makes sense here to probably round to the nearest year. I don't know that we can use partial, okay? We can't probably say, oh, these people died in July of whatever year. We probably don't know that accurately. Probably rounding to the nearest year makes the most sense. So we can say, oh, this sample is about 32,331 years old. Okay, this subject died about 32,300 something years ago. Probably, scientists would probably not even round it to the nearest whole number. They'd probably round to like the nearest 100 or maybe 1,000. So they might even say, oh, this subject died 32,000 years ago. Okay? All right. Another example. Half-life of a radioactive cobalt is 5.27 years. That means it takes 5.27 years for half of it to decay. 100 grams of radioactive cobalt is present now. How much will be present in 20 years? Okay, we need the rate. All right, because basically I know we use PERT, so there's continuous decay there. We know we start with 100. Okay. We know we're looking for 20 years, but we don't know the rate. And then if we know the rate and the time, we could plug that in here. We could figure out how much will be there 20 years later. Okay? So we need the rate. Okay. Well, we had a formula that said rate, and we're dealing with our half-lives. Remember that the rate is ln 1/2 divided by the half-life. Okay. So ln 1/2, or ln 0.5, divided by the half-life. They told us the half-life is 5.27. So my rate will be ln 0.5 divided by 5.27. So my rate is negative 0.1315. I probably should use that entire value, okay? But if I round off, if I go 4 or 5 decimals, I'm probably okay. Negative 0.1315. That's my rate, okay? It is negative because the amount of material is declining. It's decaying. So if that's my rate, then I know I started with 100. I've got my E, that's a number. Rate is negative 0.1315 times 20, because they want to know how much is there in 20 years. I can type this in my calculator, and that should tell me how much I end with in 20 years. So 100 times e to the negative 0.1315 times 20. Put that entire exponent in parentheses if you're using an 83. Okay, and we get 7.2. So the amount should be about 7.2 grams. So in 20 years, we will have about 7.2 grams. Okay. All right. Iodine 131 is a medicine that they give people with hyperthyroidism. Okay. Has a half-life of about 8 days. That means in 8 days, half of the material, half of the medicine will have decayed in your body, and you will probably need another dose. Okay. So they want the rate. They want R. Now, also, I want to point out they want the exact value. So that means it will not be okay when we find the rate to round it off. They want us to leave it in the exact form. Okay. So remember, our rate, since we're doing half-lives, okay, is going to be ln of 1/2. I'm going to put ln 0.5 divided by the half-life. So ln 0.5 divided by 8, because they told me it was 8 days. Now, this is my exact value. If I type it in my calculator, ln of 0.5, and then divide that by 8, I get a decimal. But they told me to use the exact, so I'm going to leave it like this. Make sure on your homework that you read carefully. Do they want exact? They want you to leave it in the ln format? Or do they want to round it off decimal, in which case you could type it in and get your rounded off value? Okay. How long will it take for a 100-gram sample to decay to 60 grams? Okay, so if you think about your PERT formula, we're starting with 100, that's our P, and we're ending with 60, that's our A. E to the RT. Now my rate, I'm not going to use my rounded off decimal. They told me to use that ln of 0.5 over 8, and then that number has to get multiplied by the time. That entire thing, that ln 0.5 over 8t, that whole thing is my exponent. Okay. All right, solving for e, so I'm going to divide by 100. 60 divided by 100 is 0.6. 0.6 equals e to the ln 0.5 over 8 times t. Remember, that whole thing is an exponent. Solving for e, so I need to convert to a log. Log base e, that means ln, of 0.6 equals ln 0.5 over 8 times t. Solving for t, so I got to get rid of this coefficient. I could divide by it, or I could multiply by the reciprocal. Okay, I'm going to multiply by the reciprocal. ln 0.5 over 8. So I'm going to multiply by that, and that will get t alone. If I multiply the right by ln 0.5 over 8, I got to multiply the left by ln 0.5 over 8. So in my calculator, watch this. I'm going to do ln 0.6, and that's getting multiplied by ln 0.5 divided by 8. Now notice I had to put a 0.5, parentheses around my 0.5, divided by 8, and then I have a big old closed parentheses around that whole thing to represent that that's the fraction that was multiplying by that ln 0.6. Okay. Uh-oh, I have a typo somewhere. Oh, I see it. Good grief. Having a moment. Sorry. When I had my ln 0.6 equals ln 0.5 over 8 times t. I'm sorry. When I multiplied, I should have multiplied by the reciprocal. Sorry, by 8 over ln 0.5. Because remember, when the cross-canceling leaves t alone. So I have to multiply by 8 over ln 0.5. That was the issue. My apologies. ln 0.6 times 8 over ln 0.5. And there's my 5.89, or I'm going to round it to 5.9. Okay? So that means it would take about 5.9 days. And the reason I know it's days is because that's the unit that they gave us here. So it will decay in 5.9 days. Or I'm sorry, it will take 5.9 days to go from 100 grams to 60 grams in the sample. Okay. Radioactive isotope iron 52, so it's used in medical imaging, probably like a CAT scan or MRI or something like that, has a half-life of about 8.2 hours. That means in 8.2 hours, half of the material will decay. Find the rate. Remember, rate, when we're doing half-lives, is ln 0.5 over whatever the half-life time was. So ln 0.5 divided by 8.2. So our rate, oh, and they also said they use exact. So we'll leave it as ln 0.5 over 8.2. That's the exact. If they wanted you to use a round off a decimal, you would get the negative 0.08 whatever. Okay? It is negative because it's a decay. Right? If 8 microcuries, now microcurie is just some sort of unit, grams, ounces, whatever they measure this material in, they measure it in microcuries. So if 8 of them are given to a patient, how many microcuries are left after 12 hours? Okay. Notice this half-life was in hours, so it's good that these units of time match. Okay. So the amount at the end equals our starting amount times e to the RT. And they asked us how many are left. So they're asking us for A, the amount at the end. Started with 8 times e to the RT. The rate was the ln 0.5 over 8.2. That's a fraction, and that whole thing is the exponent. And then we still need our time. They told us the time was 12. So that whole thing, ln 0.5 over 8.2 times 12, that whole thing is an exponent. So I'm going to say 8 times e to the, and I'm going to have to put, ln 0.5 divided by 8.2, and then that answer gets multiplied by 12. Okay? And we get 2.9. So if they give the person 8 microcuries, then in 12 hours, they will only have 2.9 left in their body. Okay, so in other words, if they needed to get another dose when it goes below 3 microcuries or something like that, then it would be time for them to get another dose. If they don't need another dose until it's down to 1, then it would not be time yet for another dose. So that's how the doctors would have to look and see, okay, how long does it take to decay to determine how many hours the patient needs their next dose in. Okay. The Rhind papyrus, named after Henry Rhind, contains most of what we know today of ancient Egyptian mathematics. We learned a lot about that. It was pretty cool what they found on that. A chemical analysis of a sample from the papyrus has shown that it contains about 75% of its original carbon-14. And they tell us that the half-life of carbon is 5,715. That's what they want us to use. Okay. So what is the age? So we're looking for T of the Rhind papyrus. Well, that means we need to solve for T. Well, if we're solving for T, then that means I know A, P, and R. They never told me the R, so I'm going to have to find that. Okay, remember to find the R. It's in half-lives, so ln of 0.5 divided by whatever the half-life is. And they told us the half-life was 5715. Okay. So I know that we end with 75% of whatever we started with. So I'm going to pretend that I started with 1. If I started with 1, then 75% of 1 is 0.75. So my ending amount is the 0.75. I'm using that little trick that I did over here with the 0.02. You're ending with 2%. So basically you're starting with 1 and ending with the 0.02. That's a little trick I can use. And that way it's basically like a 1 for P, and I don't even have to put it. To the R, R is ln 0.5 over 5715 times T. Remember that whole thing, ln 0.5 over 5715 T, that whole thing is my exponent. So to solve this, I'll convert to a log. Log base E, or ln, of 0.75 equals ln 0.5 over 5715 times T. Okay. I can divide by ln 0.5 over 5715, or I can multiply by the reciprocal, 5715 over ln 0.5. It's probably easier to multiply by the reciprocal. That leaves T alone. If I multiply the right side by the reciprocal, I have to multiply the left side by the reciprocal. So notice what's happening. ln of 0.75 is being multiplied by 5715 over ln 0.5. And we get 237, I'm going to say 2372 if we round to the nearest whole number. But you'll have to read what they want you to round to, okay? So the age of that Rhine papyrus is 2,372 years old. Bones of a prehistoric man found in the desert of New Mexico contain approximately 5% of the original amount. Half-life is this many years. How long ago did the man die? It's exactly like this one. We need to find R, and it will be ln of 0.5 over whatever the half-life is, 5715. So if we want to know the age of the man, he ended with 0.05 of whatever we started with. So we started with 1, ended with 0.05 of E to the ln 0.5 over 5715 times T. Convert to a log. ln 0.05 equals ln 0.5 over 5715 times T. Multiply both sides by the reciprocal, 5715 over ln 0.5. That will get T alone. So ln 0.05 multiplied by 5715 over ln 0.5. And we get 24699.8. So if we round to the nearest whole number, it would be 24,700. So that man died about 24,700 years ago.